to Topics in Geoscience. I am Fatima Abuduufu, and on today's show, Lindsay and Chris will be demonstrating 2 experiments that you can perform at home. Part 1 will explore the size of impact craters with simple objects you might have around the house. Part 2 will examine a common crater you probably did not know was an extremophile, or an organism that thrives where most others would get sick or die. First up, Lindsay and Chris will demonstrate an experiment you can do to learn more about impact craters.
Hi, I'm Lindsay.
And I'm Chris.
And today we're going to talk to you about impact craters. Whenever we take a look at images of other planetary bodies in the solar system, be they moons or other terrestrial planets, one of the features that leaps out is the impact crater, which is something that we do not see very often on the surface of Earth. And we can tell something about the age of a planetary surface by the number of impact craters. But what can we tell about a planetary surface based on the size of those impact craters? Today, we'd like to demonstrate a do-at-home experiment involving the formation of impact craters. We have a few props here. We have an aluminum tray. We have some sand. We also have a ruler and some ball bearings. And these are just metal balls of 2 different sizes. And we are going to use these to generate impact craters. Now, if you're doing this yourself at home, you could use a sandbox, you could use a beach. And if you don't have any sand, you could use something else granular, such as sugar or salt. And if you don't have metal ball bearings, you could use anything small and spherical. Marbles and golf balls would be great things to use. So for our first demonstration today, we're going to take 2 ball bearings of different sizes and drop them into the sand from the same height so that we can see if they form different sized craters. Chris? Okay. It looks like they do. So if this was a real impact situation, the velocities involved would have been much higher and the bolides would have exploded and vaporized upon impact. But since we had slower speeds, we're going to have to pick out the ball bearings from our craters. Try not to disrupt the crater too much there. Okay. And now we can measure the diameter of our crater. And let's use centimeters here since we're doing science. So would you say that's about 10 centimeters across there for the big one?
It's about 10.
So we'll write that on the board. And the little one here?
Looks like it's right around
6. Okay, so we had a much larger crater, a 10 centimeter crater for the larger ball bearing, and a 6 centimeter crater for the smaller ball bearing. We're going to write down our observation for the larger one, and we're going to repeat that experiment to make sure that it is repeatable, that we'll get the same size crater each time we try it. Okay, let's try that again to make sure that our measurements are repeatable. So Chris, if you can bring both ball bearings back and drop them from the same height and make 2 new craters. And if you're having a hard time seeing your impact craters and making these measurements, it can sometimes be helpful to use an external light, such as a flashlight, to really show a contrast between the tops and the bottoms of the craters. Centimeters again? 10 centimeters?
10. It's just about
5. Okay. Okay, so once again, we end up with two different size craters. Let me pick out those impactors again very carefully. Don't want to end up with ball bearings in the bottom of our sand. Okay, so Chris, if you want to measure those. You have the flashlight so we can see them a little more clearly too. Okay. This one, I'd say this one is, let's try two different angles here. I think that's 10 again. That's 10. And this little one, ooh, this one's a little bit, about 5.5. Yeah. So a little bit different. So we'll record those. Chris is gonna drop the two ball bearings again. Same height. Okay. And we once again have our impact craters. Very, very carefully removing the impactors. And taking our measurements. Centimeters.
It's 10 again.
That's pretty consistent. That is 10. Ooh, this one's up to 6.
Yeah.
So 10 centimeters for the big one and 6 for the small one. Now let's record our measurements.
Lindsay and Chris' experiments provide us with the data I have on the whiteboard here. Later, we were able to add more data to these first findings by dropping the large ball bearings from a ladder 3 meters above the pen. They then used a slingshot to increase the velocity of the ball bearings. To further illustrate the effects of these impacts, we added some tempera paint to the top of the sand before dropping or shooting the ball. We will now take a look at some of slow motion footage we acquired during these other tests. It appears to be the case that it's not just the size of the impactor that determines the size of the crater, but its velocity also needs to be taken into consideration. When we are looking at planetary surfaces, this can complicate things, since we cannot easily distinguish between craters produced by large impactors moving relatively slowly and those produced by smaller impactors colliding at greater speeds. Next, we will return to Chris and Lindsay for an experiment where we try to learn more about extremophile organisms and their importance to the growing field of astrobiology.
Hi, I'm Lindsay,
And I'm Chris.
and today we're here to talk to you about extremophile organisms, which are organisms that can exist under really harsh conditions on Earth. And they are important for the emerging field of astrobiology, which is the study of the origin, evolution, development, distribution, and future of life in the universe. On Earth, it doesn't seem to matter just how hot or how cold or how dry or how acid or how salty an environment is. There are organisms that can live in all of those environments. And it doesn't matter where you are, if you're beneath the ice in Antarctica or if you're in volcanic gases, you can still have organisms that can survive in those contexts. And this has implications for the distribution of life in the universe, because if these types of environments are habitable, then perhaps there could be habitable environments on worlds like Europa or Mars or elsewhere in the solar system. So today we're going to be focusing on one extremophile organism in particular, the brine shrimp. Chris, can you tell us something about brine shrimp?
Sure. The brine shrimp are an example of halophiles, or salt-loving organisms. Some of these are even found in the Great Salt Lakes in Utah, which can be up to 10 times saltier than even the ocean. They have gills, just like other fish, and have a special gland that helps them filter out unwanted salt. You might have heard of these before. They're commonly used as fish food, and kids know them as sea monkeys.
Thanks. And what we have for you today is a little thing labeled brine shrimp eggs. We purchased this online. You can also buy something like this at a pet store that sells fish. And what it is a little container, a little vial that has dormant sea monkey eggs. And these are really cysts, and they're dried out, and you can store these for years. You can freeze these, and when you come ready to make your fish food, all you have to do is add them to salt water, and some of them will hatch. So this means that you can have these in an environment like a salt lake that dries out sometimes. They can dry out entirely and come back as soon as water is present. So we're going to see what it takes to make these grow. So what do we need? We need about a half liter of water. Got it?
Almost.
And the recipe calls for, the recipe on the back says for 1 liter, so we're doing a half batch here. Adding it to our beaker. That was just tap water. We also need a half teaspoon of eggs. Open the vial here. Up to 50. You only have to fill up to 50.
Isn't it 10?
No.
Well, we're at about 5.
Okay.
Yeah.
And add that. And 1 tablespoon of salt. And we're using a fairly coarse salt. One thing you want to make sure if you're trying this at home, don't use iodized salt. You want to use sea salt without iodine. Better for these things to grow in. And if we were really following the instructions on the back, we would have purchased an aeration system to keep the solution oxygenated as they grew. We do not have that here today. We have found doing this in the past that some of them will come to life without that. So now we can give this a stir. Okay, that's probably good enough. You can pull that out. Okay, so our first solution is ready to go. So we took the brine shrimp straight out of the container, and we put them into the water. We added the salt, and we basically just followed the package directions. So that was our control case. Now, for the fun part. We are going to set up another experiment that is going to test just how resistant these brine shrimp eggs to different nasty conditions. What else should we try, Chris?
Well, how about microwaving them? See how they react to microwave radiation?
Okay, so what's our hypothesis?
Well, I'd say at least some of them will hatch even after being exposed to the radiation.
Okay, let's give it a try. Should we just put this beaker in the microwave then?
No, that really wouldn't work. It wouldn't really be testing the hypothesis since we'd be both heating up the water and exposing them to microwave radiation. So if none of them hatch, we wouldn't know which factor actually caused them not to hatch.
Okay, so perhaps we should be doing it dry. So let's measure out our half teaspoon again, 5 milliliters. And we are going to put those into a microwave. Okay. So, I guess we have to do it on this side. How long should we do it for, Chris?
Say a minute.
Okay, so that produced a little more smoke than we were anticipating, but we can still test this. I wonder if some of these are still going to survive after having been bombarded by microwave radiation for a full minute. Let's measure out some water. So 500 milliliters again?
Yep.
Okay.
Another tablespoon of salt.
A tablespoon of salt, and let's see if this sizzles.
It did.
Yes, it does. Whew. I'm just going to use a little stick here to get as many of these cooked brine shrimp eggs in here as possible. Let's not forget our salt, since these are halophile organisms. They like their salt.
Should be good.
Should be good. Okay, so now we have our control case and our test case. Let's make sure to label them, so if we come back in a few days, we will know which one was which. So Chris is labeling them right now, control and test. Great. Now we could sit here and watch these, but that might get a little boring. The container says it's going to take about 24 to 36 hours for them to start to hatch. In my experience, especially if we're doing it without aeration, it can take as much as 5 days to start to see them, so that we might get a little bored waiting for them to hatch. So we'll put them aside and check in on them later. Okay, let's get this out of the way. Okay, now fortunately we planned ahead, and so rather than having you sit there for 24 hours and wait for these to hatch, we have one that we set up last week that we know it hatched. So let's go take a look at that new beaker.
Well, they really are quite tiny, aren't they?
Yeah, sometimes if you have a hard time seeing them, if you shine a light, a flashlight or something at them, you can get them to swim towards the light. So if you're having a hard time finding them, that might be a trick to try. So if you're trying this at home, I recommend setting up at least 2 experiments. One control case where you follow the recipe, and one where you change just one parameter, the temperature, sunlight, something like that, the salinity, something like that. Either some extreme condition that you are subjecting your eggs to, or some difference in the conditions of the setup, so that you're testing and isolating one variable and seeing how that affects the ability of the sea monkeys to hatch. We used microwave radiation here, but you can come up with your own hypothesis if you want, using some different form of harsh treatment for the cysts or unusual conditions for them to grow in.
So Lindsay, what does this have to do with astrobiology?
Well, if if life could exist in such harsh environments on Earth, maybe it could have survived in really harsh environments on the surface of early Mars, or perhaps even in the sub-ice oceans on Europa and Ganymede, two of the moons of Jupiter. And if dormant eggs can survive radiation and extremely cold temperatures and perhaps vacuum, then perhaps they could survive in the interior of rocks that were blasted off of one planet, which might fall on another planet as meteoroids. There was even an experiment that was being conducted on the Space Shuttle Columbia when it did not survive re-entry in 2003, and the nematodes, a type of worm, actually survived and were recovered from the wreckage of the space shuttle.
Wow. Extremophiles really are quite extreme.
And